you want to make a love note here to yourself that cofactor expansion is simply a shorthand to the recursive definition of the determinant that we've been looking at. It's also going to provide us with some fun new features. So let's take a minute and look at our definition, and we'll go through some examples. So if we let A be some n by n matrix, we can then say that the ith jth cofactor of A is defined as capital C sub ij. And we can rewrite this, actually give ourselves a little bit more room. C sub ij, so this is equal to -1 raised to the I plus 1 multiplied by the determinant of the submatrix A sub ij. And again, we know that we can alternatively write this using the alternative notation of the determinant. And we recognize this. This is the same form we use with our recursive definition. So keeping this cofactor in mind here, we can now rewrite the determinant of an n by n matrix A as follows. So we have the determinant of matrix A is equal to the entry A sub 1, 1 multiplied by the cofactor C sub 1, 1 plus A sub 1, 2 multiplied by the cofactor A sub 1, 2. And this process continues all the way up to the last entry in the first row and column multiplied by the corresponding cofactor. And so we want to make a love note here to ourselves before we proceed that this is simply the cofactor expansion across the first row of A, just like we were doing with the recursive definition. So we have the cofactor expansion across row 1, or the first row of matrix A, which is equivalent to the recursive definition. Now, what makes cofactor expansion so much fun is that it can be performed across any row and or down any column. Right, so this is going to simplify our computational lives substantially. We can look at some n by n matrix A and determine what column or what row is going to produce the easiest computations for us. So let's take a quick peek at each case here. So we can apply cofactor expansion across the ith row of a matrix. And in this case, we have that the determinant of matrix A is defined by the cofactor expansion. And we have the entry in the ith row first column multiplied by the cofactor in the ith row first column plus the entry in the ith row second column times the cofactor sub I2 plus la la la. We continue all the way up until we have the entry in the ith row nth column times the corresponding cofactor. And then alternatively, we now have cofactor expansion down the jth column. And in this case, we can write the determinant of A as the entry in the first row jth column times the corresponding cofactor plus the entry in the second row jth column times the cofactor, or the corresponding cofactor. And we continue all the way until we get to the entry in the nth row jth column times the corresponding cofactor. And again, we love this method because it gives us the option to either expand across a row if we want, or expand down a column if we want. So I really encourage you to look at the given matrix and determine what's going to be the easiest for you. And that being said, there's going to be multiple correct ways to approach different questions here to find the determinant, but just be mindful that if your computation is getting ugly quickly, try another row or column.